Okay, so let's try to solve this problem, palindromic partitioning 2. So this problem says that given a string S, partition S such that every substring of the partition is a palindrome. Return the minimum cards needed for a palindromic partitioning of S. Example, S is equal to AAB and output is 1. So minimum cards is 1 because we can put a card between AA and B, right? So AA and B both are palindrome, okay? S for S equal to A, so there is there is only one character, so you cannot put a cut in between, so that's why it's 0, so output would be 0. If the input is AB, then we can only put a card between A and B, so that's why the output will be 1. Okay, and the constant has been mentioned as the string length is greater than is equal to 1 and less than is equal to 2000. Okay, is consists of lowercase English letters only. Okay, so there are only lowercase English letters. Okay, before solving this problem, I would suggest you please watch my previous video based on the palindromic partitioning 1, which is which was 131 palindromic partitioning. Now, what is the intuition behind this problem? So intuition is, first we need to get all the possible palindromic partitions of S. Okay, next we need to find the minimum number of cards needed for a palindromic partition of S. Okay, so first we need to get all the palindromic partitions, and then we need to find like what is the minimum number of cards we can put, so that the partitions we got, so they all the partitions are palindrome. So over here, right, get all the possible palindromic partitions. So this I think we solved using recursion, then backtracking, and then we optimized with dynamic programming. Okay, then now in this problem we need to find the minimum number of cards. So when there is minimum of something or maximum something keywords are found, so we can think of taking we can think of approaching with dynamic programming, but we need to check. Okay, so it's not always like we should be approaching with dynamic programming only. So let's take an example, AAB. Okay, at maximum we can put cards after every character, so in that case cards will be, number of cards will be 2. Okay, so number of cards is 2. Okay, which is nothing but the string length, which is 3 minus 1. So it is this is the number of cards, but these are the this is the maximum number of cards, right? But we need to find the minimum number of cards. Okay, so in that case we can put a card after A. Okay, now we can use a formula, minimum cards is equal to minimum of number of cards. Okay, number of cards comma cards found so far plus find cards for the remaining substring. Okay, so here minimum cards is minimum of, so current cards we found as 2. Okay, cards found so far is 1. Okay, so we have put a card over after A, so that's why cards found so far is 1, plus find cards for the remaining substring. So substring starting with, so substring find cards for substring starting with start plus 1 to end. Okay, now now over here, right, so after we already absorbed the string like A, so we cannot do any other operation on A, right? So then we need to move forward with other parts of the string. Okay, so in that case we can put a card after A. So this was already absorbed, now we put a card after A, B. So in that case what will be the minimum number of cards? So minimum would be 2, 1 plus find the cards for the substring starting with start to end. So this we found as 1. We cannot put a card after the end of the string, so that's why we can put this is our end, like we cannot put any more cards over here. Okay, so in that case the minimum number of cards would be 2, 2. So this minimum of 2, 2 is 2. Okay, but this is not the answer, because we need to find 1. So this is the maximum number of cards. Again we got the maximum number of cards only. After putting a card after every character. Okay, so so then we need to go back to the original string, right? So we need to go back to the original string, which was AB. Okay, AB. Okay, now this time we will put a card after AA. Okay, not after A. Okay, so in this case what will be the cards? So in this case will be minimum number of cards will be minimum of number of cards, so which was 2. Okay, already we calculated over here 2. Okay, number of cards. Okay, and then find cards for the remaining substring. So cards found so far we already put a card over here 1. Okay, and find the cards for the remaining substring. So remaining substring is B. Okay, so and we cannot put a card after B, so in that case it will be 0 only. So if we are calculating minimum of 2, 1, so which is 1 only, and this is the answer we expect. Okay, okay, now we can see over here, like when we are finding the minimum number of cards in our first approach, right, after putting a card after A, then we first calculated for the first part A, and then again iteratively we are or recursively we are finding the cards for the remaining part of the substring. Okay, but we could not find. Okay, so in that case we could not find the minimum number of cards. So again we go back to the original string. So this is when we go back to the original string, so this is, we can say, like we have backtracked. Okay, so this we have backtracked. Okay, so and when you are searching, when you are finding for the remaining part of the strings, we are doing recursively. So this is recursion. Okay, so both are combinations of pairing together, recursion and backtracking. Okay, so using recursion and backtracking we can find the minimum number of cuts. Okay, okay, but we need to optimize. So we need to optimize using so if you are simply following with recursion backtracking, then the complexity, time complexity will be exponential. So I mean then we can get in TLE, like time limit exceeded error. Okay, so we need to optimize, and that constant has been mentioned, string length has been mentioned as 2000 maximum string length. So I mean, at least we should we should write our code such that it should have a time complexity of O of n square. Okay, right? Okay, so let's try to write the code in, let's try to approach first in recursion and backtracking, and then we'll optimize with dynamic programming. Okay, so let's discuss the approach. Okay, so first we'll declare a function which will say whether the particular portion of the string is palindrome or not. So you can say like if each palindrome, it will expect 3 parameters: start, end, and the string. Okay, now as we generally do, I mean our general approach. So while start less than equal to end, if s of start not equal to s of end, okay, then simply return false. Okay, start plus plus and minus minus. Okay, and once we are out of the loop, then we can return true. Okay, so basically we have taken a 2 pointer and we are moving towards each other. Okay, so and we are checking each of the character, okay, at every point, like whether it is same or not. If it is not same, then simply return false. If it is same, then simply return. If it is, I mean, if we could not find a false option, or if it is every character is same in the both the in the part of the string, then we can simply return true. Okay, so this is done. We'll go to the second option, okay, to find the minimum number cards. Okay, so again we'll take a function, okay, which will expect 3 parameters: start, end, and this string s. Okay, and this is a recursive function. Okay, so we need to put a base case. So base case would be if start equal to end. So if we have our start is reached to the end position, then we can simply return, or the string we are finding, that is already a palindrome, right? So in that case we can, if each palindrome start, end, s, okay, then we can simply return 0. Okay, this is done. Okay, so this is base case is done. Okay, now what is the minimum number, what is the cards currently, number of cards currently? So current cards we have is, so you can declare a variable minimum cards is the cards between n minus start, okay, like we had found over here. Okay, so minimum cards is n minus start, so which is 3 initially. It would be like 3 minus 1, or we can say like 2 minus 0, which is 2. This is 2. Okay, so start, basically initially we started with 0 position, and the end is a 3 length character a b, right? 3 length string, right? So it is length is 3, so 0 1 2, so 2 minus 0 is 2. Okay, so this is the number of cards, okay, currently. Okay, then what we'll do, we'll run a loop and we'll take a variable current index, so which will denote the end of the current substring. Okay, so we'll run a loop car index. Okay, so car index will start from car index equal to start, and will run till end of the substring. Okay, current index less than equal to end car index plus plus. Okay, and now this car index, as I already said, right, the car index will point the end of the current substring. Okay, but we are starting from start, so we are starting from start and this is our current index. Okay, so we need to find this particular substring is palindrome or not. Okay, so we'll call this function if is palindrome, our start position is start. Okay, and end is current index. Okay, string is the s. Okay, so you can call this function. Okay, and this will return whether the particular substring is palindrome or not, and then we need to find the minimum cuts. Okay, so in this case minimum cuts is equal to minimum of min cuts. Okay, which is 2 over here, and then 1 plus f of car index plus 1 comma end comma s. So we simply call this function recursively. Okay, so we need to find the remaining part of the substring. Okay, so this will return the minimum cuts. Okay, and once we are out of the loop, so we can simply return minimum cuts. Okay, okay, and this will be this will be our recursive function to solve, to get the minimum number cuts for the palindrome partitioning of a string. Okay, now what would be the time complexity for this? So time complexity would be 2 to the power n. Okay, and we are also calculating whether a string is palindrome or not, so in that case another n. Okay, so this is the time complexity. Space complexity would be we are using an auxiliary stack space, so it is O of n. I mean, this auxiliary stack space is for recursion only, right? Okay, so let's draw the recursion tree now. Okay, and find like whether we are having any overlapping subproblems, right? So recursion tree. Okay, so let's take an example a b. Okay, so if we decide we will put a card after a, then remaining tree is ab. If we backtrack and then decide like we will not put a card after a, we'll put card after a b, then this is a and b. Okay, and the last option would be a. If we decide like we will not put a card after a, then we can put a card after a b, but this is the end of the string, right? So you cannot put a card over here. Okay, next is, okay, so for this we can again put a card after a b. Okay, again we decide like we will not put a card over here, we will put a card after a b, and over here where this is end of the string, so you cannot put a card over here. Okay, for this we can put a card after a and b, but again this is end of the string, so you can put a card after end of the string. Okay, then finally what we have, we have this one, Okay, so A, and after that B is the remaining string, and after B you can put a card, but again this is a end of the string. So you can see over here number of cards is 2 and number of cards is 1 over here. And what is the minimum? So minimum is 1, so 1 is the answer. Now we can see like over here, right, we are over here and over here, right, we are calculating B twice, right, we are calculating for B twice. Okay, and when there are overlapping subproblems, like when there is when we are calculating again and again, then we can optimize with dynamic programming, right? And in dynamic programming we generally have two approaches. One is top down dynamic programming, so which is memoization plus recursion. Okay, and bottom up dynamic programming, which is tabulation. Okay, so in bottom up dynamic programming, in the sense like we first store the values in a table, we first look for the smaller problems and then store the values in a table, and when we are moving to the next step we refer to the same values again whatever we store in the table. Okay, and so it is basically from smaller to larger problems, right? So this is smaller to larger problems, that's why we call bottom up. And then top down dynamic programming is basically we look for the larger problems and then we store the values or memorize the values in a table, and when we find the same problem again, we find the same problem again, we refer the memoized value from the table. Okay, so first we'll solve using the top down dynamic programming, and then we'll look for the bottom up dynamic programming. Okay, so let's solve using top down dynamic programming. Okay, so for top down dynamic programming we'll have two DP tables. Okay, so one is with size n into n and another is for palindrome DP, which will again store which will have size n into n. Okay, so first this will be keeping the cards, the number of cards for a string starting with start and end. Okay, and and this will store like whether a particular string starting with a start and end is palindrome or not. Okay, okay, so but over here so you can see over here you can see like this n parameter is right, so this n parameter is not changing, so only the changing parameter is start, right? So in this case we can think of having only one DDP array only. I think 1 DDP array will suffice. Okay, so we don't need a 2 DDP array. Okay, this DP array will initialize with -1. Okay, and this DP array will initialize with false. Okay, okay, now let's optimize the first function, which is the utility function, to check whether the string is palindrome or not. So let's optimize that. So is palindrome, and we are expecting two parameters. We are and expect 3 parameters: start, end, and S. Okay, now first we will check whether we already pre-computed the string or the substring, whether it's a palindrome or not. So in that case we can simply refer this particular DP. Okay, so a palindrome DP start end it's true, then we can simply return palindrome DP of start end. Okay, now we'll copy the loop. Okay, so while start less than is equal to end, and over here we will say like if s of start not is equal to s of end, then simply return false. You already done this, right? And we'll increment the start pointer from left and we'll decrement the end pointer from right. Okay, so this is done, and at the end out of the loop, when you're out of the loop, we'll say return dp of palindrome dp of start end is equal to true. So this part we optimized. Okay, so each palindrome function we optimize using memoization. Okay, now we'll go to our actual function, which returns the minimum number of cards. Okay, so in that function we will pass start end s and one more parameter. So what parameters we had over here? Start end and s, and now extra parameter will pass as dp. Okay, now for this what I will do, so first we'll copy the base case. So base case, okay, so if start is equal to end or is palindrome, the substring is already palindrome, then the cards will be 0, right? So is palindrome start end and s. Okay, so in that case return 0. So this is done. Okay, base case we copied. Next we will check you already memoized the value or not. If dp of start not is equal to -1, then simply return dp of start. Okay, this will return the memoized value. Else whatever the loop we are doing, starting from the current we are starting from the start to current index, that will execute again. So for current index is equal to start current index less than is equal to end car index plus plus. Okay, and what we will do over here, okay, before that we need to store the minimum cards. So minimum cards is equal to n minus start, we'll keep same. Okay, now over here what we will do is minimum cards is equal to minimum of min cards comma 1 plus f of car index plus 1 and start end comma dp. Okay, so this is done. Okay, will be out of the loop, and before returning from this function we will store the result into the dp table or the dp array, 1D array, whatever you have taken, and over there we will keep dp of start is equal to minimum cards. Okay, so this we optimized. Okay, so using memoization, and finally we will call this f start in this this function f with 0, end will be s of the length -1 and s, okay, the string, and pass the dp. Okay, so this will give our result. Okay, I think I forgot to call the function over here in our first approach, in the recursive approach. It will be same. I think we could already figure it out. So over here it will be f 0, start is 0, end is s dot length or size -1 based on the programming language, and then pass the string. Okay, now for this memoized approach or the top down dp approach, so what is the time complexity? So time complexity would be O of n square. Okay, and then we are O of n square, and then we are also running a loop to check whether it's a palindrome or not, so that we can say like O of n square into n. Okay, and space complexity would be O of n. So you have we are already using a dp table to store the cards, number of cards. Okay, so that will take O of n. Then we are storing, we are taking a 2D dp array to store, to pre-compute whether a substring is palindrome or not. So for that it will be O of n square. Then we are also using a auxiliary stack space for recursion, right? So in that case it is O of n. So this is aux. Okay, this is for palindrome dp, and this is for the dp to store the number of cards, right, for a string, for a particular substring. Okay, so and so in this case the effective will be, we can say, O of n square space complexity. This will remain same. Okay, O of n square into n, or n into n square. Okay, we can say whatever you want. Okay, so this tabulation, this top down approach is done. Now we'll move forward to tabulation. Okay, so tabulation we already said, like from smaller sub problems to larger sub problems. Okay, so in this case we'll initialize our we'll have a 1D dp array of size n, and with initialize with 0. Okay, and we'll take same dp same 2D dp array for palindrome substrings. So then we'll have a size n into n, and we'll initialize with false. Okay, like the whatever we had done earlier. Okay, but only thing, like in this case we are initializing the dp array, 1D dp array as 0, and this we are and this we kept same. Okay, now what we will do, now we'll solve the smaller problems first, and then we'll move forward for the larger problems. Okay, so in this case we'll run a loop. So for end equal to 0, end less than h dot length, end plus plus. Okay, and we'll store the minimum cuts. So minimum cuts is equal to end. So if we'll run another loop, in a loop, start is equal to 0, and this will run till end, start less than equal to end, start plus plus. Okay, this is done. Okay, now in this case we should refer the approach we have taken in the palindrome partitioning 1 problem. Okay, so I'll refer the same thing over here. So I mean the optimized way how we pre-computed, how we are storing on the fly, how we are storing the substring value on the fly on the palindrome tree. So that we should refer over here. So we'll copy almost the same thing over here. Okay, so it will be s of start. If you still face problem to understand, I would suggest to watch the previous video on this actually, and it has a detailed description about this, detailed explanation about this. Okay, so if f of s of start is equal to s of end and end minus start less than is equal to 2, okay, or palindrome dp of start plus 1 and end minus 1 is true, right? Basically the inner string is already palindrome, the outer string will be also a palindrome. I think we already discussed about this. Okay, so then we can say like palindrome dp of start end equal to true. Okay, right? So then this is true. Okay, so if the inner string is palindrome, outer string is palindrome, right? Now we'll calculate the minimum cuts. So in that case minimum cuts is equal to, if start is equal to 0, if the start is 0 then it will be 0 only, right? So if start is equal to 0, then it is 0, minimum number of cuts is 0. Okay, else we'll calculate the minimum of current min cuts, comma, whatever we calculated till the previous end, which is start minus 1 will append 1 after that. So basically previous up to this whatever cards we found, so that will calculate whatever we stored into the dp table, and then we'll add 1 because we are currently putting one more card, right? Because we found a palindrome, so this will add 1 over here. Okay, now we'll store dp of, before this outer loop ends, we'll store dp of end is equal to minimum cuts. Okay, and finally we'll return dp of h dot length or h dot size based on the programming language, h dot size minus 1. Okay, so this will be the answer. Okay, and what will be the time complexity for this? So time complexity would be O of n square. We are running a loop, 2 loops over here. Space complexity would be O of n square. Okay, because we are using a 2D DP array and another 1D DP array, which is O of n. So effective we can say like it is O of n square only. Okay, my bad, O of n square. Okay.